An incandescent light bulb, incandescent lamp or incandescent light globe is an electric light which produces light with a wire filament heated to a high temperature by an electric current passing through it, until it glows. The hot filament is protected from oxidation with a glass or quartz bulb that is filled with inert gas or evacuated. In a halogen lamp, filament evaporation is prevented by a chemical process that redeposits metal vapor onto the filament, extending its life. The light bulb is supplied with electrical current by feed-through terminals or wires embedded in the glass. Most bulbs are used in a socket which provides mechanical support and electrical connections. Incandescent bulbs are manufactured in a wide range of sizes, light output, and voltage ratings, from 1.5 volts to about 300 volts. They require no external regulating equipment, have low manufacturing costs, and work equally well on either alternating current or direct current. As a result, the incandescent lamp is widely used in household and commercial lighting, for portable lighting such as table lamps, car headlamps, and flashlights, and for decorative and advertising lighting. Incandescent bulbs are much less efficient than most other types of electric lighting. Incandescent bulbs convert less than 5% of the energy they use into visible light. The luminous efficacy of a typical incandescent bulb is 16 lumens per watt, compared to the 60 lumina per watt of a compact fluorescent bulb. Some applications of the incandescent bulb deliberately use the heat generated by the filament. Such applications include incubators, brooding boxes for poultry, heat lights for reptile tanks, infrared heating for industrial heating and drying processes, lava lamps, and the Easy Bake Oven toy. Incandescent bulbs also have short lifetimes compared with other types of lighting. Around 1,000 hours for home light bulbs versus up to 10,000 hours for compact fluorescents and up to 100,000 hours for LED lamps. Incandescent bulbs are gradually being replaced in many applications by other types of electric light, such as fluorescent lamps, compact fluorescent lamps, cold cathode fluorescent lamps, high-intensity discharge lamps, and light-emitting diode lamps. Some jurisdictions, such as the European Union and Canada, are in the process of phasing out the use of incandescent light bulbs. History. In addressing the question of who invented the incandescent lamp, historians Robert Friedel and Paul Israel list 22 inventors of incandescent lamps prior to Joseph Swan and Thomas Edison. They conclude that Edison's version was able to outstrip the others because of a combination of three factors: an effective incandescent material, a higher vacuum than others were able to achieve, and a high resistance that made power distribution from a centralized source economically viable. Historian Thomas Hughes has attributed Edison's success to his development of an entire, integrated system of electric lighting. The lamp was a small component in his system of electric lighting, and no more critical to its effective functioning than the Edison jumbo generator, the Edison main and feeder, and the parallel distribution system. Other inventors with generators and incandescent lamps, and with comparable ingenuity and excellence, have long been forgotten because their creators did not preside over their introduction in a system of lighting. Early pre-commercial research. In 1802, Humphrey Davy had what was then the most powerful electrical battery in the world at the Royal Institution of Great Britain. In that year, Davy created the first incandescent light by passing the current through a thin strip of platinum, chosen because the metal had an extremely high melting point. It was not bright enough nor did it last long enough to be practical, but it was the precedent behind the efforts of scores of experimenters over the next 75 years. Over the first three-quarters of the 19th century, many experimenters worked with various combinations of platinum or iridium wires, carbon rods, and evacuated or semi-evacuated enclosures. Many of these devices were demonstrated and some were patented. In 1835, James Bowman Lindsay demonstrated a constant electric light at a public meeting in Dundee, Scotland. He stated that he could read a book at a distance of 1.5 feet. However, having perfected the device to his own satisfaction, he turned to the problem of wireless telegraphy and did not develop the electric light any further. His claims are not well documented, although he is credited in Challoner Ale with being the inventor of the incandescent light bulb. In 1840, British scientist Warren de la Roux enclosed a coiled platinum filament in a vacuum tube and passed an electric current through it. The design was based on the concept that the high melting point of platinum would allow it to operate at high temperatures and that the evacuated chamber would contain fewer gas molecules to react with the platinum, improving its longevity. Although a workable design, the cost of the platinum made it impractical for commercial use. In 1841, Frederick de Molyens of England was granted the first patent for an incandescent lamp, with a design using platinum wires contained within a vacuum bulb. In 1845, American John W. Starr acquired a patent for his incandescent light bulb involving the use of carbon filaments. He died shortly after obtaining the patent, and his invention was never produced commercially. Little else is known about him. In 1851, Jean Huguenet Robert Houdin publicly demonstrated incandescent light bulbs on his estate in Blois, France. His light bulbs are on display in the Museum of the Car Cento de Blois. In 1872, Russian Alexander Ladygin invented an incandescent light bulb and obtained a Russian patent in 1874. He used as a burner 2 carbon rods of diminished section in a glass receiver, hermetically sealed, and filled with nitrogen, electrically arranged so that the current could be passed to the second carbon when the first had been consumed. Later he lived in the USA, changed his name to Alexander de Ladygin and applied and obtained patents for incandescent lamps having chromium, iridium, rhodium, ruthenium, osmium, molybdenum and tungsten filaments, and a bulb using a molybdenum filament was demonstrated at the World Fair of 1900 in Paris. Heinrich Gar Paragraph Bell in 1893 claimed he had designed the first incandescent light bulb in 1854, with a thin carbonized bamboo filament of high resistance, platinum lead-in wires in an all-glass envelope, and a high vacuum. Judges of 4 courts raised doubts about the alleged Gar Paragraph Bell anticipation, but there was never a decision in a final hearing due to the expiry date of Edison's patent. A research work published 2007 concluded that the story of the Gar Paragraph Bell lamps in the 1850s is a legend. On July 24, 1874, a Canadian patent was filed by Henry Woodward and Matthew Evans for a lamp consisting of carbon rods mounted in a nitrogen-filled glass cylinder. They were unsuccessful at commercializing their lamp, and sold rights to their patent to Thomas Edison in 1879. Commercialization. Joseph Swan was a British physicist and chemist. In 1850, he began working with carbonized paper filaments in an evacuated glass bulb. By 1860, he was able to demonstrate a working device, but the lack of a good vacuum and an adequate supply of electricity resulted in a short lifetime for the bulb and an inefficient source of light. By the mid-1870s better pumps became available, and Swan returned to his experiments. With the help of Charles Stern, an expert on vacuum pumps, in 1878, Swan developed a method of processing that avoided the early bulb blackening. This received a British patent in 1880. On December 18, 1878, a lamp using a slender carbon rod was shown at a meeting of the Newcastle Chemical Society, and Swan gave a working demonstration at their meeting on January 17, 1879. It was also shown to 700 who attended a meeting of the Literary and Philosophical Society of Newcastle upon Tyne on February 3, 1879. These lamps used a carbon rod from an arc lamp rather than a slender filament. Thus they had low resistance and required very large conductors to supply the necessary current, so they were not commercially practical, although they did furnish a demonstration of the possibilities of incandescent lighting with relatively high vacuum, a carbon conductor, and platinum lead-in wires. Besides requiring too much current for a central station electric system to be practical, they had a very short lifetime. Swan turned his attention to producing a better carbon filament and the means of attaching its ends. He devised a method of treating cotton to produce parchmentized thread and obtained British patent 4933 in 1880. From this year he began installing light bulbs in homes and landmarks in England. His house was the first in the world to be lit by a light bulb and so the first house in the world to be lit by hydroelectric power. In 1878 the home of Lord Armstrong at Cragside was also among the first houses to be lit by electricity. In the early 1880s he had started his company. In 1881, the Savoy Theatre in the city of Westminster, London was lit by Swan incandescent light bulbs, which was the first theatre, and the first public building in the world, to be lit entirely by electricity. Thomas Edison began serious research into developing a practical incandescent lamp in 1878. Edison filed his first patent application for improvement in electric lights on October 14, 1878. After many experiments, first with carbon in the early 1880s and then with platinum and other metals, in the end Edison returned to a carbon filament. The first successful test was on October 22, 1879, and lasted 13.5 hours. Edison continued to improve this design and by November 4, 1879, filed for a U.S. patent for an electric lamp using a carbon filament or strip coiled and connected to platina contact wires. Although the patent described several ways of creating the carbon filament including using cotton and linen thread, with splints, papers coiled in various ways, Edison and his team later discovered that a carbonized bamboo filament could last more than 1,200 hours. Hiram S. Maxim started a light bulb company in 1878 to exploit his patents and those of William Sawyer. His United States Electric Lighting Company was the second company, after Edison, to sell practical incandescent electric lamps. In 1880, the Oregon Railroad and Navigation Company's steamer, Columbia, became the first application for Edison's incandescent electric lamps. Columbia sank in a collision with a schooner off California in 1907. The first commercial installation of incandescent lamps was made at the Mercantile Safe Deposit Company in New York City in the fall of 1880, about 6 months after the Edison incandescent lamps had been installed on the Columbia. In October 1880, Maxim patented a method of coating carbon filaments with hydrocarbons to extend their life. Louis Latimer, employed at the time by Edison, developed an improved method of heat-treating carbon filaments which reduced breakage and allowed them to be molded into novel shapes, such as the characteristic M shape of Maxim filaments. On January 17, 1882, Latimer received a patent for the process of manufacturing carbons, an improved method for the production of light bulb filaments, which was purchased by the United States Electric Light Company. Latimer patented other improvements such as a better way of attaching filaments to their wire supports. In Britain, the Edison and Swan companies merged into the Edison and Swan United Electric Company. Edison was initially against this combination, but after Swan sued him and won, Edison was eventually forced to cooperate, and the merger was made. Eventually, Edison acquired all of Swan's interest in the company. Swan sold his U.S. patent rights to the Brush Electric Company in June 1882. In 1882, the first recorded set of miniature incandescent lamps for lighting a Christmas tree was installed. These did not become common in homes for many years. The United States Patent Office gave a ruling October 8, 1883, that Edison's patents were based on the prior art of William Sawyer and were invalid. Litigation continued for a number of years. Eventually on October 6, 1889, a judge ruled that Edison's electric light improvement claim for a filament of carbon of high resistance was valid. In the 1890s, the Austrian inventor Karl Auer von Welsbach worked on metal filament mantles, first with platinum wire, and then osmium, and produced an operating version in 1898. In 1898, he patented the osmium lamp and started marketing it in 1902, the first commercial metal filament incandescent lamp. In 1897, German physicist and chemist Walther Nernst developed the Nernst lamp, a form of incandescent lamp that used a ceramic globe and did not require enclosure in a vacuum or inert gas. Twice as efficient as carbon filament lamps, Nernst lamps were briefly popular until overtaken by lamps using metal filaments. In 1901, American businessman Frank A. Poore purchased the Merit Manufacturing Company, the predecessor to North American light bulb makers Highgrade and Osram Sylvania. Poore's firm in Middleton, Massachusetts, specialized in refilling burned-out light bulbs until 1916. In 1903, Willis Whitney invented a metal-coated carbon filament that would not blacken the inside of a light bulb. Tungsten bulbs. On December 13, 1904, Hungarian Zajanda Just and Croatian Franjo Hahnemann were granted a Hungarian patent for a tungsten filament lamp that lasted longer and gave brighter light than the carbon filament. Tungsten filament lamps were first marketed by the Hungarian company Tungsram in 1904. This type is often called Tungsram bulbs in many European countries. Their experiments also showed that the luminosity of bulbs filled with an inert gas was higher than in vacuum. The tungsten filament outlasted all other types. In 1906, the General Electric Company patented a method of making filaments from sintered tungsten and in 1911, used ductile tungsten wire for incandescent light bulbs. In 1913, Irving Langmuir found that filling a lamp with inert gas instead of a vacuum resulted in twice the luminous efficacy and reduction of bulb blackening. In 1924, Marvin Pitkin, an American chemist, patented a process for frosting the inside of lamp bulbs without weakening them, and in 1947, he patented a process for coating the inside of lamps with silica. Between 1924 and the outbreak of the Second World War, the Phoebus cartel attempted to fix prices and sales quotas for bulb manufacturers outside of North America. In 1930, Hungarian Imbra Cube DY filled lamps with krypton gas rather than argon, and designed a process to obtain krypton from air. Production of krypton-filled lamps based on his invention started at Orsia in 1937, in a factory co-designed by Polonese and Hungarian-born physicist Egon Roux. By 1964, improvements in efficiency and production of incandescent lamps had reduced the cost of providing a given quantity of light by a factor of 30, compared with the cost at introduction of Edison's lighting system. Consumption of incandescent light bulbs grew rapidly in the U.S. In 1885, an estimated 300,000 general lighting service lamps were sold, all with carbon filaments. When tungsten filaments were introduced, about 50 million lamp sockets existed in the U.S. In 1914, 88.5 million lamps were used, and by 1945, annual sales of lamps were 795 million. Efficacy, efficiency, and environmental impact. Of the power consumed by typical incandescent light bulbs, 95% or more is converted into heat rather than visible light. Other electrical light sources are more effective. Luminous efficacy of a light source may be defined in two ways. The radiant luminous efficacy is the ratio of the visible light flux emitted to the total power radiated over all wavelengths. The source luminous efficacy is the ratio of the visible light flux emitted to the total power input to the source, such as a lamp. Visible light is measured in lumens, a unit which is defined in part by the differing sensitivity of the human eye to different wavelengths of light. Not all wavelengths of visible electromagnetic energy are equally effective at stimulating the human eye. The luminous efficacy of radiant energy is a measure of how well the distribution of energy matches the perception of the eye. The units of luminous efficacy are lumens per watt. The maximum LER possible is 683 a lumen per watt for monochromatic green light at 555 nanometers wavelength, the peak sensitivity of the human eye. The luminous efficiency is defined as the ratio of the luminous efficacy to the theoretical maximum luminous efficacy of 683 lpw, and, as for luminous efficacy, is of two types, radiant luminous efficiency and source luminous efficacy. The chart below lists values of overall luminous efficacy and efficiency for several types of general service, 120-volt, 1,000-hour lifespan incandescent bulb, and several idealized light sources. The values for the incandescent bulbs are source efficiencies and efficacies. The values for the ideal sources are radiant efficiencies and efficacies. A similar chart in the article on luminous efficacy compares a broader array of light sources to one another. The spectrum emitted by a blackbody radiator at temperatures of incandescent bulbs does not match the sensitivity characteristics of the human eye. The light emitted does not appear white, and most is not in the range of wavelengths at which the eye is most sensitive. Tungsten filaments radiate mostly infrared radiation at temperatures where they remain solid below 3695 K. Donald L. Klipstein explains it this way: an ideal thermal radiator produces visible light most efficiently at temperatures around 6300 degrees Celsius. Even at this high temperature, a lot of the radiation is either infrared or ultraviolet, and the theoretical luminous efficacy is 95 lumens per watt. No known material can be used as a filament at this ideal temperature, which is hotter than the sun's surface. An upper limit for incandescent lamp luminous efficacy is around 52 lumens per watt, the theoretical value emitted by tungsten at its melting point. Although inefficient, incandescent light bulbs have an advantage in applications where accurate color reproduction is important, since the continuous blackbody spectrum emitted from an incandescent light bulb filament yields near-perfect color rendition, with a color rendering index of 100. White balancing is still required to avoid too warm, or cool colors, but this is a simple process that requires only the color temperature in Kelvin as input for modern, digital visual reproduction equipment such as video or still cameras unless it is completely automatized. The color rendering performance of incandescent lights cannot be matched by LEDs or fluorescent lights, although they can offer satisfactory performance for non-critical applications such as home lighting. White balancing such lights is therefore more complicated, requiring additional adjustments to reduce for example green-magenta color casts, and even when properly white balanced, the color reproduction will not be perfect. For a given quantity of light, an incandescent light bulb produces more heat than a fluorescent lamp. In buildings where air conditioning is used, incandescent lamps' heat outputs increases load on the air conditioning system. Heat from lights will displace heat required from a building's heating system, but generally space heating energy is of lower cost than heat from lighting. High-quality halogen incandescent lamps have higher efficacy, which will allow a halogen light to use less power to produce the same amount of light compared to a non-halogen incandescent light. The expected lifespan of halogen lights is also generally longer compared to non-halogen incandescent lights, and halogen lights produce a more constant light output over time, without much dimming. There are many non-incandescent light sources, such as the fluorescent lamp, high-intensity discharge lamps and LED lamps, which have higher luminous efficiency, and some have been designed to be retrofitted in fixtures for incandescent lights. These devices produce light by luminescence. These mechanisms produce discrete spectral lines and do not have the broad tail of invisible infrared emissions. By careful selection of which electron energy level transitions are used, and fluorescent coatings which modify the spectral distribution, the spectrum emitted can be tuned to mimic the appearance of incandescent sources, or other different color temperatures of white light, although due to the discrete spectral lines rather than a continuous spectrum, the color rendering index will not be perfect for applications such as photography or cinematography. Cost of lighting. The initial cost of an incandescent bulb is small compared to the cost of the energy it uses over its lifetime. Incandescent bulbs have a shorter life than most other lighting, an important factor if replacement is inconvenient or expensive. Some types of lamp, including incandescent and fluorescent, emit less light as they age. This may be an inconvenience, or may reduce effective lifetime due to lamp replacement before total failure. A comparison of incandescent lamp operating cost with other light sources must include illumination requirements, cost of the lamp and labor cost to replace lamps, cost of electricity used, effective lamp operation on heating and air conditioning systems. When used for lighting in houses and commercial buildings, the energy lost to heat can significantly increase the energy required by a building's air conditioning system, although during the heating season such heat is not all wasted, but is not as effective as the heating system. Measures to ban use. Since incandescent light bulbs use more energy than alternatives such as CFLs and LED lamps, many governments have introduced measures to ban their use, by setting minimum efficacy standards higher than can be achieved by incandescent lamps. In the U.S., federal law has scheduled the most common incandescent light bulbs to be phased out by 2014, to be replaced with more energy-efficient light bulbs. Traditional incandescent light bulbs were phased out in Australia in November 2009. Objections to banning the use of incandescent light bulbs include the higher initial cost and quality of light of alternatives. Some people have concerns about the health effects of fluorescent lamps. Efforts to improve efficiency. Some research has been carried out to improve the efficacy of commercial incandescent lamps. In 2007, the Consumer Lighting Division of General Electric announced a high-efficiency incandescent lamp project, which they claimed would ultimately be as much as 4 times more efficient than current incandescents, although their initial production goal was to be approximately twice as efficient. The HEI program was terminated in 2008 due to slow progress. U.S. Department of Energy research at Sandia National Laboratories initially indicated the potential for dramatically improved efficiency from a photonic lattice filament. However, later work indicated that initially promising results were in error. Prompted by U.S. legislation mandating increased bulb efficiency by 2012, new hybrid incandescent bulbs have been introduced by Philips. The halogen energy saver incandescent is 30% more efficient than traditional designs, using a special chamber to reflect formerly wasted heat back to the filament to provide additional lighting power. Construction. Incandescent light bulbs consist of an airtight glass enclosure with a filament of tungsten wire inside the bulb, through which an electric current is passed. Contact wires and a base with 2 conductors provide electrical connections to the filament. Incandescent light bulbs usually contain a stem or glass mount anchored to the bulb's base that allows the electrical contacts to run through the envelope without air or gas leaks. Small wires embedded in the stem in turn support the filament and its lead wires. The bulb is filled with an inert gas such as argon and nitrogen to reduce evaporation of the filament and prevent its oxidation at a pressure of about 70 kPa. Early lamps, and some small modern lamps used only a vacuum to protect the filament from oxygen. An electric current heats the filament at typically 2000 to 3300 K, well below tungsten's melting point of 3695 K. Filament temperatures depend on the filament type, shape, size, and amount of current drawn. The heated filament emits light that approximates a continuous spectrum. The useful part of the emitted energy is visible light, but most energy is given off as heat in the near-infrared wavelengths. 3-way light bulbs have 2 filaments and 3 conducting contacts in their bases. The filaments share a common ground, and can be lit separately or together. Common wattages include 30 euro 70 euro 100, 50 euro 100 euro 150, and 100 euro 200 euro 300. With the first 2 numbers referring to the individual filaments, and the third giving the combined wattage. Most light bulbs have either clear or coated glass. The coated glass bulbs have a white powdery substance on the inside called kaolin. Kaolin, or kaolinite, is a white, chalky clay in a very fine powder form, that is blown in and electrostatically deposited on the interior of the bulb. It diffuses the light emitted from the filament, producing a more gentle and evenly distributed light. Manufacturers may add pigments to the kaolin to adjust the characteristics of the final light emitted from the bulb. Kaolin-diffused bulbs are used extensively in interior lighting because of their comparatively gentle light. Other kinds of colored bulbs are also made, including the various colors used for party bulbs, Christmas tree lights and other decorative lighting. These are created by staining the glass with a dopant, which is often a metal like cobalt or chromium. Neodymium-containing glass is sometimes used to provide a more natural-appearing light. Many arrangements of electrical contacts are used. Large lamps may have a screw base or a bayonet base. Some tubular lamps have an electrical contact at either end. Miniature lamps may have a wedge base and wire contacts, and some automotive and special-purpose lamps have screw terminals for connection to wires. Contacts in the lamp socket allow the electric current to pass through the base to the filament. Power ratings for incandescent light bulbs range from about 0.1 watt to about 10,000 watts. The glass bulb of a general service lamp can reach temperatures between 200 and 260 degrees Celsius. Lamps intended for high-power operation or used for heating purposes will have envelopes made of hard glass or fused quartz. Manufacturing. Early lamps were laboriously assembled by hand. After automatic machinery was developed, the cost of lamps fell. In manufacturing the glass bulb, a type of ribbon machine is used. A continuous ribbon of glass is passed along a conveyor belt, heated in a furnace, and then blown by precisely aligned air nozzles through holes in the conveyor belt into molds. Thus the glass bulbs are created. After the bulbs are blown, and cooled, they are cut off the ribbon machine. A typical machine of this sort produces 50,000 bulbs per hour. The filament and its supports are assembled on a glass stem, which is fused to the bulb. The air is pumped out of the bulb, and the evacuation tube in the stem press is sealed by a flame. The bulb is then inserted into the lamp base, and the whole assembly tested. Filament. The first successful light bulb filaments were made of carbon. Early carbon filaments had a negative temperature coefficient of resistance as they got hotter, their electrical resistance decreased. This made the lamp sensitive to fluctuations in the power supply, since a small increase of voltage will cause the filament to heat up, reducing its resistance and causing it to draw even more power and heat even further. In the flashing process, carbon filaments were heated by current passing through them, while in an evacuated vessel containing hydrocarbon vapor. The carbon deposited by this treatment improved the uniformity and strength of filaments, and their efficiency. A metallized or graphitized filament was first heated in a high-temperature oven before flashing and lamp assembly. This transformed the carbon into graphite, which further strengthened and smoothed the filament, and as a byproduct had the advantage of changing the lamp to a positive temperature coefficient like a metallic conductor. This helped stabilize power consumption, temperature and light output against minor variations in supply voltage. In 1902, the Siemens company developed a tantalum lamp filament. These lamps were more efficient than even graphitized carbon filaments and could operate at higher temperatures. Since the metal had a lower resistivity than carbon, the tantalum lamp filament was quite long and required multiple internal supports. The metal filament had the property of gradually shortening in use. The filaments were installed with large loops that tightened in use. This made lamps in use for several hundred hours quite fragile. Metal filaments had the property of breaking and re-welding, though this would usually decrease resistance and shorten the life of the filament. General Electric bought the rights to use tantalum filaments and produced them in the U.S. until 1913. From 1898 to around 1905, osmium was also used as a lamp filament in Europe, but the metal was so expensive that used broken lamps could be returned for part credit. It could not be made for 110V or 220V, so several lamps were wired in series for use on standard voltage circuits. In 1906, the tungsten filament was introduced. Tungsten metal was initially not available in a form that allowed it to be drawn into fine wires. Filaments made from sintered tungsten powder were quite fragile. By 1910, a process was developed by William D. Coolidge at General Electric for production of a ductile form of tungsten. The process required pressing tungsten powder into bars, then several steps of sintering, swagging, and then wire drawing. It was found that very pure tungsten formed filaments that sagged in use, and that a very small doping treatment with potassium, silicon, and aluminium oxides at the level of a few hundred parts per million greatly improved the life and durability of the tungsten filaments. To improve the efficiency of the lamp, the filament usually consists of coils of coiled fine wire, also known as a coiled coil. For a 60-watt 120-volt lamp, the uncoiled length of the tungsten filament is usually 22.8 inches, and the filament diameter is 0.0018 inches. The advantage of the coiled coil is that evaporation of the tungsten filament is at the rate of a tungsten cylinder having a diameter equal to that of the coiled coil. The coiled coil filament evaporates more slowly than a straight filament of the same surface area and light emitting power. If the filament is then run hotter to bring back evaporation to the same rate, the resulting filament is a more efficient light source. There are several different shapes of filament used in lamps, with differing characteristics. Manufacturers designate the types with codes such as C6, CC-6, C2V, CC-2V, C8, CC-88, C2F, CC-2F, C-bar, C-bar 6, C8I, C2R, CC-2R, and axial. Electrical filaments are also used in hot cathodes of fluorescent lamps and vacuum tubes as a source of electrons or in vacuum tubes to heat an electron-emitting electrode. Reducing filament evaporation. One of the problems of the standard electric light bulb is evaporation of the filament. Small variations in resistivity along the filament cause hot spots to form at points of higher resistivity. A variation of diameter of only 1% will cause a 25% reduction in service life. The hot spots evaporate faster than the rest of the filament, increasing resistance at that point. A positive feedback that ends in the familiar tiny gap in an otherwise healthy-looking filament. Irving Langmuir found that an inert gas, instead of vacuum, would retard evaporation. General service incandescent light bulbs over about 25 watts in rating are now filled with a mixture of mostly argon and some nitrogen, or sometimes krypton. Since a filament breaking in a gas-filled bulb can form an electric arc, which may spread between the terminals and draw very heavy current, intentionally thin lead-in wires or more elaborate protection devices are therefore often used as fuses built into the light bulb. More nitrogen is used in high-voltage lamps to reduce the possibility of arcing. While inert gas reduces filament evaporation, it also conducts heat from the filament, thereby cooling the filament and reducing efficiency. At constant pressure and temperature, the thermal conductivity of a gas depends upon the molecular weight of the gas and the cross-sectional area of the gas molecules. Higher molecular weight gases have lower thermal conductivity, because both the molecular weight is higher and also the cross-sectional area is higher. Xenon gas improves efficiency because of its high molecular weight, but is also more expensive, so its use is limited to smaller lamps. During ordinary operation, the tungsten of the filament evaporates. Hotter, more efficient filaments evaporate faster. Because of this, the lifetime of a filament lamp is a trade-off between efficiency and longevity. The trade-off is typically set to provide a lifetime of several hundred to 2,000 hours for lamps used for general illumination. Theatrical, photographic, and projection lamps may have a useful life of only a few hours, trading life expectancy for high outputs in a compact form. Long-life general service lamps have lower efficiency but are used where the cost of changing the lamp is high compared to the value of energy used. Filament notching describes another phenomenon that limits the life of lamps. Lamps operated on direct current develop random stair-step irregularities on the filament surface, reducing the cross-section and further increasing heat and evaporation of tungsten at these points. In small lamps operated on direct current, lifespan may be cut in half compared to AC operation. Different alloys of tungsten and rhenium can be used to counteract the effect. If a light bulb envelope leaks, the hot tungsten filament reacts with air, yielding an aerosol of brown tungsten nitride, brown tungsten dioxide, violet-blue tungsten pentoxide, and yellow tungsten trioxide that then deposits on the nearby surfaces or the bulb interior. Bulb blackening. In a conventional lamp, the evaporated tungsten eventually condenses on the inner surface of the glass envelope, darkening it. For bulbs that contain a vacuum, the darkening is uniform across the entire surface of the envelope. When a filling of inert gas is used, the evaporated tungsten is carried in the thermal convection currents of the gas, depositing preferentially on the uppermost part of the envelope and blackening just that portion of the envelope. An incandescent lamp that gives 93% or less of its initial light output at 75% of its rated life is regarded as unsatisfactory, when tested according to IEC publication 60064. Light losses due to filament evaporation and bulb blackening. Study of the problem of bulb blackening led to the discovery of the Edison effect, thermionic emission and invention of the vacuum tube. A very small amount of water vapor inside a light bulb can significantly affect lamp darkening. Water vapor dissociates into hydrogen and oxygen at the hot filament. The oxygen attacks the tungsten metal, and the resulting tungsten oxide particles travel to cooler parts of the lamp. Hydrogen from water vapor reduces the oxide, reforming water vapor and continuing this water cycle. The equivalent of a drop of water distributed over 500,000 lamps will significantly increase darkening. Small amounts of substances such as zirconium are placed within the lamp as a getter to react with any oxygen that may bake out of the lamp components during operation. Some old, high-powered lamps used in theater, projection, searchlight, and lighthouse service with heavy, sturdy filaments contained loose tungsten powder within the envelope. From time to time, the operator would remove the bulb and shake it, allowing the tungsten powder to scrub off most of the tungsten that had condensed on the interior of the envelope, removing the blackening and brightening the lamp again. Halogen lamps. The halogen lamp reduces uneven evaporation of the filament and darkening of the envelope by filling the lamp with a halogen gas at low pressure, rather than an inert gas. The halogen cycle increases the lifetime of the bulb and prevents its darkening by redepositing tungsten from the inside of the bulb back onto the filament. The halogen lamp can operate its filament at a higher temperature than a standard gas-filled lamp of similar power without loss of operating life. Such bulbs are much smaller than normal incandescent bulbs, and are widely used where intense illumination is needed in a limited space. Fiber optic lamps for optical microscopy is one typical application. Incandescent arc lamps, a variation of the incandescent lamp, did not use a hot wire filament, but instead used an arc struck on a spherical bead electrode to produce heat. The electrode then became incandescent, with the arc contributing little to the light produced. Such lamps were used for projection or illumination for scientific instruments such as microscopes. These arc lamps ran on relatively low voltages and incorporated tungsten filaments to start ionization within the envelope. They provided the intense concentrated light of an arc lamp but were easier to operate. Developed around 1915, these lamps were displaced by mercury and xenon arc lamps. Electrical characteristics, power. Incandescent lamps are nearly pure resistive loads with a power factor of 1. This means the actual power consumed and the apparent power are equal. Incandescent light bulbs are usually marketed according to the electrical power consumed. This is measured in watts and depends mainly on the resistance of the filament, which in turn depends mainly on the filament's length, thickness, and material. For two bulbs of the same voltage, type, color, and clarity, the higher-powered bulb gives more light. The table shows the approximate typical output, in lumens, of standard incandescent light bulbs at various powers. Light output of a 230V version is usually slightly less than that of a 120V version. The lower current filament is thinner and has to be operated at a slightly lower temperature for same life expectancy, and that reduces energy efficiency. The lumen values for soft white bulbs will generally be slightly lower than for clear bulbs at the same power. Current and resistance. The actual resistance of the filament is temperature dependent. The cold resistance of tungsten filament lamps is about 1/15 the hot filament resistance when the lamp is operating. For example, a 100-watt, 120-volt lamp has a resistance of 144 ohms when lit, but the cold resistance is much lower. Since incandescent lamps are resistive loads, simple phase control TRIAC dimmers can be used to control brightness. Electrical contacts may carry a T rating symbol indicating that they are designed to control circuits with a high inrush current characteristic of tungsten lamps. For a 100-watt, 120-volt general service lamp, the current stabilizes in about 0.10 seconds, and the lamp reaches 90% of its full brightness after about 0.13 seconds. Physical characteristics, bulb shapes. Incandescent light bulbs come in a range of shapes and sizes. The names of the shapes may be slightly different in some regions. Many of these shapes have a designation consisting of one or more letters followed by one or more numbers, for example, A55 or PAR38. The letters represent the shape of the bulb. The numbers represent the maximum diameter either in 1/8 of an inch, or in millimeters, depending on the shape and the region. For example, 63-on reflectors are designated R63, but in the US, they are known as R20. However, In both regions, a PAR38 reflector is known as PAR38. Common shapes, general service, light emitted in all directions. Available either clear or frosted. Types: general, mushroom, elliptical, sine, tubular, 120V sizes, A17, 19 and 21, 230V sizes, A55 and 60, high wattage general service, lamps greater than 200 watts. Types: pear-shaped, decorative, lamps used in chandeliers, etc. Types: candle, twisted candle, bent-tip candle, flame, globe, lantern chimney, fancy round, 230V sizes, P45, G95, reflector, reflective coating inside the bulb directs light forward. Flood types spread light. Spot types concentrate the light. Reflector bulbs put approximately double the amount of light on the front central area as general service of same wattage. Types: standard reflector, elliptical reflector, crown silvered, 120V sizes, R16, 20, 25 and 30, 230V sizes, R50, 63, 80 and 95, parabolic aluminized reflector. Parabolic aluminized reflector bulbs control light more precisely. They produce about 4 times the concentrated light intensity of general service, and are used in recessed and track lighting. Weatherproof casings are available for outdoor spot and flood fixtures. 120V sizes, PAR16, 20, 30, 38, 56 and 64, 230V sizes, PAR16, 20, 30, 38, 56 and 64, available in numerous spot and flood beam spreads. Like all light bulbs, the number represents the diameter of the bulb in 1/8 of an inch. Therefore, a PAR16 is 2 in diameter, a PAR20 is 2.5 in diameter, PAR30 is 3.75 in and a PAR38 is 4.75 in diameter. Multifaceted reflector, HIR. HIR is a GE designation for a lamp with an infrared reflective coating. Since less heat escapes, the filament burns hotter and more efficiently. The OSRAM designation for a similar coating is IRC. Lamp bases. Very small lamps may have the filament support wires extended through the base of the lamp, and can be directly soldered to a printed circuit board for connections. Some reflector-type lamps include screw terminals for connection of wires. Most lamps have metal bases that fit in a socket to support the lamp and conduct current to the filament wires. In the late 19th century, manufacturers introduced a multitude of incompatible lamp bases. General Electric introduced standard base sizes for tungsten incandescent lamps under the Mazda trademark in 1909. This standard was soon adopted across the U.S., and the Mazda name was used by many manufacturers under license through 1945. Today most incandescent lamps for general lighting service use an Edison screw and candelabra, intermediate, or standard or mogul sizes, or double-contact bayonet base. Technical standards for lamp bases include ANSI standard C81.67 and IEC standard 60061-1 for common commercial lamp sizes, to ensure interchangeability between different manufacturers' products. Bayonet base lamps are frequently used in automotive lamps to resist loosening due to vibration. A bipin base is often used for halogen or reflector lamps. Lamp bases may be secured to the bulb with a cement, or by mechanical crimping to indentations molded into the glass bulb. Miniature lamps used for some automotive lamps or decorative lamps have wedge bases that have a partial plastic or even completely glass base. In this case, the wires wrap around to the outside of the bulb, where they press against the contacts in the socket. Miniature Christmas bulbs use a plastic wedge base as well. Lamps intended for use in optical systems such as film projectors, microscope illuminators, or stage lighting instruments have bases with alignment features so that the filament is positioned accurately within the optical system. A screw-base lamp may have a random orientation of the filament when the lamp is installed in the socket. Light output and lifetime. Incandescent lamps are very sensitive to changes in the supply voltage. These characteristics are of great practical and economic importance. For a supply voltage V near the rated voltage of the lamp, this means that a 5% reduction in operating voltage will more than double the life of the bulb, at the expense of reducing its light output by about 20%. This may be a very acceptable trade-off for a light bulb that is in a difficult-to-access location. Long-life bulbs take advantage of this trade-off. Since the value of the electric power they consume is much more than the value of the lamp, general service lamps emphasize efficiency over long operating life. The objective is to minimize the cost of light, not the cost of lamps. Early bulbs had a life of up to 2,500 hours, but in 1924 a cartel agreed to limit life to 1,000 hours. When this was exposed, the limitation was banned in 1953. The relationships above are valid for only a few % change of voltage around rated conditions, but they do indicate that a lamp operated at much lower than rated voltage could last for hundreds of times longer than at rated conditions, albeit with greatly reduced light output. The Centennial Light is a light bulb that is accepted by the Guinness Book of World Records as having been burning almost continuously at a fire station in Livermore, California, since 1901. However, the bulb uses only 4 watts. A similar story can be told of a 40-watt bulb in Texas that has been illuminated since September 21, 1908. It once resided in an opera house where notable celebrities stopped to take in its glow, and was moved to an area museum in 1977. In flood lamps used for photographic lighting, the trade-off is made in the other direction. Compared to general service bulbs, for the same power, these bulbs produce far more light, and light at a higher color temperature, at the expense of greatly reduced life. The upper temperature limit for the filament is the melting point of the metal. Tungsten is the metal with the highest melting point, 3695 Ka. A 50-hour life projection bulb, for instance, is designed to operate only 50 AA degrees Celsius below that melting point. Such a lamp may achieve up to 22 lumens per watt, compared with 17.5 for a 750-hour general service lamp. Lamps designed for different voltages have different luminous efficacy. For example, a 100-watt, 120-volt lamp will produce about 17.1 lumens per watt. A lamp with the same rated lifetime but designed for 230 V would produce only around 12.8 lumens per watt, and a similar lamp designed for 30 volts would produce as much as 19.8 lumens per watt. Lower voltage lamps have a thicker filament, for the same power rating. They can run hotter for the same lifetime before the filament evaporates. The wires used to support the filament make it mechanically stronger, but remove heat, creating another trade-off between efficiency and long life. Many general service 120-volt lamps use no additional support wires, but lamps designed for rough service, or vibration service may have as many as 5. Low-voltage lamps have filaments made of heavier wire and do not require additional support wires. Very low voltages are inefficient since the lead wires would conduct too much heat away from the filament, so the practical lower limit for incandescent lamps is 1.5 volts. Very long filaments for high voltages are fragile, and lamp bases become more difficult to insulate, so lamps for illumination are not made with rated voltages over 300 volts. Some infrared heating elements are made for higher voltages, but these use tubular bulbs with widely separated terminals. See also. References. External links. Light source spectra 60W 100 watts incandescent light bulb spectra, from Cornell University Program of Computer Graphics, Bulb Museum.